Hi everyone. Hi everyone. Today in this video we will discuss the new chapter, that is oscillations. What is meant by oscillation and one important characteristics of that, one important types of oscillation that here we are going to discuss, that is known as simple harmonic motion. Okay, all those things that we are going to discuss here. So first of all we will discuss about what is meant by periodic motion. Periodic motion means a motion. The motion which repeats at regular intervals of time is known as periodic motion. And next we are going to discuss about oscillatory motion. The motion in which an object moves about its mean position in to and fro or back and forth motion following the same path, that is known as oscillatory motion. And next one is vibratory motion. Vibratory motion means the oscillatory motion of an object about its mean position with high frequency. So if the oscillatory motion is taking place with high frequency, that is known as vibratory motion. So we can say that a periodic motion means motion which repeats at regular intervals of time. Any motion which repeats after a regular interval of time is known as periodic motion. And if an object is moving to and fro with respect to a mean position, that is known as oscillatory motion, and fast oscillations are known as vibration or vibratory motion. Okay. So periodic motion itself we can classify into oscillatory motion and non-oscillatory motion. And non-oscillatory motion, example, motion of moon around the earth. So in that case what happens? Even though it is periodic, that is it repeats at regular interval of time, but it is not oscillatory. It is not moving. That moon is not moving or oscillating with respect to a mean position. No, it is moving around the earth. It is periodic motion, but it is not oscillatory. And oscillatory motion itself we can classify as oscillatory motion and vibratory motion. So example of oscillatory motion, that is what is meant by oscillatory motion, to and fro motion of any object with respect to its main position. Example, simple pendulum. In that case what happens? Frequency will be low. And if it is vibratory motion, frequency will be high. For example, string of guitar about its axis, it happens that string is vibrating with very high frequency, so that motion we can call it as vibratory motion. That is also oscillatory motion only, oscillations only, but fast oscillations are there. That's why we are calling it as vibratory motion. Okay. So we can say that oscillatory and vibratory both are periodic. No, that also repeat at regular intervals of time, but all periodic motions are not oscillatory. All periodic motions are not oscillatory or vibratory, but all oscillatory or vibratory motions are periodic because it repeats at regular intervals of time. So in the example of guitar, we can say that it is vibratory. It is periodic also, it is vibratory also. But in the case of moon around the earth, we can say it is only periodic. It is not oscillatory or vibratory because the moon is not revolving. Moon is revolving around the earth, but it is not oscillating with respect to a mean position with low or high frequency. So it is not oscillatory or vibratory. It is only periodic. Okay. And another example, motion of a simple pendulum, that we can say it as oscillatory motion. Okay. So we can, this is very important thing, you have to know that all periodic motions are not oscillatory, but all oscillatory motions are periodic. Why it is periodic? Because it repeats itself at regular intervals of time. Okay, is it clear? So this is very important. All periodic motions are not oscillatory, but all oscillatory motions are periodic, or in other words we can say that either oscillatory or vibratory motions are all periodic. Okay. And now we will discuss about periodic function. So any function that repeats itself at regular intervals of argument is called a periodic function. That is, any function which repeats itself at regular intervals. At regular intervals of time. If a function repeats its value, that is known as periodic function. For example, you can see here, this is sine curve. So you can see that at when it from 0 to 2 pi, same this, after that it repeats the same graph. No, so it repeats itself at regular intervals of time. Another example is that this curve, you can see that the same graph is repeated at regular intervals of time. And another example here, you can see that this is another example. So after one cycle, after every one cycle, the same pattern will be repeated. That type of functions are known as periodic functions. Okay, function which repeats itself at regular intervals of time are known as periodic function. That is, same pattern or same shape will be repeated after a regular interval of time. Okay. And harmonic function. Harmonic function means the periodic functions which can be represented by a sine or cosine curve. Okay, any periodic function, that is any function which repeats at regular interval of time is known as periodic function, and that can be represented if we are representing that periodic function, if it is a sine or cosine curve, they are known as harmonic function. Okay, it may be either sine or cosine curve. So what's the specialty of sine or cosine curve? They can have maximum value +1 and minimum value -1. No, they can have, for either sine or cosine function, they can take maximum value of +1 and minimum value of -1. So we can say that harmonic functions can be represented only as sine or cosine curve. So harmonic functions can have maximum value, that is no, +1 or -1. Example, this is cosine curve. So you can see that at when the angle becomes 0, cosine function has maximum value. Again, when it becomes pi, it became minus value -1. Again, when it becomes 2 pi, you can see that it became +1. Okay. So this is an example of harmonic function, that is cosine graph, cosine function. And next one is sine graph, sine function. So here you can see that when sine 0, 0, sine pi is again 0, sine 2 pi is 0, sine pi by 2 is 1, and sine 3 pi by 2 is -1. So you can see that for both of these curves, they are having the maximum value +1 and minimum value is -1. So this is example of harmonic function, only sine or cosine curve. No, it is not possible tan or cot or sec. Why? Because their maximum value is not +1 and minimum value is not -1. So they are not harmonic functions. Okay, non-harmonic functions. These are also non-harmonic functions, are also periodic functions, but they cannot be represented by a single sine or cosine curve. By a sine or cosine curve, they cannot be represented. For example, this graph, you can see that it is not a single curve, single sine curve. Even it is that function is repeating itself at regular intervals of time. It is periodic function, but it is not harmonic. Similarly, this graph, here you can see that same graph is repeated at regular intervals of time, but its maximum and minimum value is not +1 or -1. Minimum value, even though it is -1, it is not a sine function. Maximum value, you can see that it is 3. Okay, so this is not a harmonic function. It is an example of non-harmonic function. Now we will discuss about simple harmonic motion. It is also known as SHM, simple harmonic motion. It is a periodic motion. The body moves to and fro about its mean position. Okay, so we can say it is a periodic motion. Body will move to and fro about its mean position. And what's the specialty in this type of periodic motion? The restoring force on the oscillating body. The restoring force acting on the body is always directly proportional to its displacement and is always directed towards its mean position. Okay. So restoring force is directly proportional to displacement and is always directed towards its displacement or towards its mean position. Such type of motion is known as simple harmonic motion. So it is a type of periodic motion in which the object is under oscillation. So when it is oscillating with respect to a mean position, so restoring force will be there, which will try to bring it back, that object, to its original position, and that restoring force will be proportional to displacement and it is acting towards the mean position. So if we try to displace the object larger, what happens? More restoring force will be there, and if we displace less restoring force will be there. So we can write restoring force is proportional to x. F is restoring force, x is displacement, or we can write F is equal to minus kx. And what negative sign shows? Negative sign shows that restoring force is in a direction opposite to the direction of displacement. F is the force, x is displacement, k is known as force constant or spring factor. So by using Newton's second law of motion, we can write F, instead of F we can write ma, mass into acceleration, is equal to minus kx, or we can write acceleration is equal to minus k by m into x, or in other words we can write acceleration is proportional to displacement. So like this also we can define simple harmonic motion. So a particle is said to possess simple harmonic motion if it moves to and fro about a mean position under an acceleration which is directly proportional to its displacement from the mean position and is always directed towards that mean position. So in that way also we can define. Okay. So if any system which satisfies this equation, we can say that is executing simple harmonic motion. Okay. And examples of simple harmonic motion: oscillations of a load, a spring, if it is oscillating, that we can consider as a simple harmonic motion. Similarly, vibrations of a tuning fork and vibrations of the balance wheel of a watch and the oscillations of a freely suspended magnet in a uniform magnetic field, all those can be considered as simple harmonic motion. Okay. Now we will discuss about the differential equation of simple harmonic motion. So we are starting from that equation. We know that force is equal to mass into acceleration, and acceleration can be written as rate of change of velocity. Again, velocity can be written as rate of change of displacement, or we can write acceleration as the second derivative of displacement. So we can write F is equal to ma, which is equal to m into d square x by dt square. And in the case of simple harmonic motion, we know F is equal to minus kx. Just now we discussed. F stands for the force, k stands for spring constant, spring factor or force constant, and x is the displacement. So we can equate both. So what you will get, m into d square x by dt square equal to minus kx, or we can write d square x by dt square equal to minus k by m into x, or instead of k by m, if we are writing it as omega square, so what you will get, d square x by dt square equal to minus omega square x, or we can write d square x by dt square plus omega square x equal to 0. And this is the differential equation for linear simple harmonic motion. Okay, this equation is very important, d square x by dt square plus omega square x equal to 0, where omega is known as angular frequency or angular velocity. Okay. So this is the differential. So how to find the solution of this equation? Normally what in quadratic equation you might have studied. Now various methods are there to find the solution of the quadratic equation. So like that, for this differential equation also different methods are there that you will study next year only in 12th. So if I am telling that this is the solution, how we can check whether it is true or not? We have to substitute that value, no? And if that value satisfies that equation, we can say that is the solution of the equation. Okay, so we can say that just I am telling that x equal to a cos omega t plus phi 0 is the solution of this differential equation. Okay, so how to check whether it is true or not? So what we have to do, x already it is there. Now we have to differentiate it two times. No, d square x by dt square we have to find. So we can differentiate it once, dx by dt we will get. Again if you differentiate, what you will get, d square x by dt square you will get. No. So dx by dt, if you differentiate, what you will get? A cosine, if you differentiate cosine function you will get minus sine omega t plus phi 0, and here omega will be there. No. If it is cos theta, if you differentiate you will get minus sine theta. Since cos omega t plus phi 0 is there, you will get it as minus omega a into sine omega t plus phi 0. No. And once again, if you differentiate, what you will get? D square x by dt square. So what you will get? Minus omega square a, and say if you differentiate sine function, you will get cosine function. So omega into omega, you will get it as omega square. So minus omega square into a cos omega t plus phi 0. Or that can be written as minus omega square into a cos omega t plus phi 0 is x. So d square x by dt square, you got it as minus omega square x, or you can write d square x by dt square plus omega square x equal to 0, which means the solution satisfies the differential equation. So we can say x equal to a cos omega t plus phi 0 is the solution of the equation. Not only cosine function, sine function also possible. Okay, instead of x equal to a cos omega t plus phi 0, we can take x equal to a sin omega t plus phi 0. That also can be considered as the solution of the differential equation, either cosine function or sine function. Okay. So x, what is x? X is the displacement of the particle. A stands for the amplitude. What is meant by amplitude? That we will discuss. Omega stands for the angular frequency or angular velocity, and phi 0 is the initial phase. That also we will discuss what is meant by those terms. Okay. So the solution of the differential equation is given by x equal to a cos omega t plus phi 0, or we can write x equal to a sin omega t plus phi 0. Either cosine, you can check. Same way you can try whether it satisfies or not. Okay. So either cosine function or sine function can be assumed as the solution of this differential equation. Okay. Now we will discuss some terms related to simple harmonic motion. First of all, we will discuss what is meant by harmonic oscillator. Harmonic oscillator means a particle executing simple harmonic motion is known as harmonic oscillator. Any particle which executes simple harmonic motion. Okay. For example, simple pendulum. Okay. That we can consider it as harmonic oscillator. Pendulum. Bob of the pendulum, that can be considered as harmonic oscillator because it executes simple harmonic motion. And displacement. Displacement means the distance of the oscillating particle from its mean position. From the mean position, what is the distance of the oscillating particle? That is known as displacement. And amplitude means the maximum displacement of the oscillating particle on either side of its mean position. That is known as amplitude. Maximum displacement is known as amplitude. And oscillation. Oscillation means one complete back and forth motion of a particle starting and ending at the same point is called a cycle or oscillation or vibration, because if we are assuming it as fast oscillation, we can say it as vibration also. Okay. So one complete back and forth motion of the particle, that is known as oscillation. Now we will discuss about period and frequency. Period means the time taken by an oscillating body to complete one cycle. Okay. To complete one cycle, how much time an oscillating body is taking, that is known as period. This means the to and fro motion of the body gets repeated after fixed interval of time. After regular interval, after every time period, after every period, that same oscillations will be repeated. And period normally we used to represent by capital letter T, and its SI unit is second. And next we are going to discuss about frequency. It is defined as number of cycles per second. Means number of oscillations in 1 second. It is we are denoting it either by nu or by F, and its SI unit is per second or hertz. And you know the relation between frequency and time period, that already we discussed in that chapter, motion in a plane. Frequency is given by 1 by time period. Okay. So these relations are very important to solve problems. Again, some more terms are there related to simple harmonic motion. Next one is angular frequency. Angular frequency or angular velocity is given by angle covered by in one time period. So 2 pi, in one time period it covers an angle 2 pi. So 2 pi by t, and 1 by t can be written as frequency. So angular velocity or angular frequency, the relation between angular frequency and time period is given by omega is equal to 2 pi by t, and the relation between angular frequency and Linear frequency is given by omega is equal to 2 pi nu or 2 pi f. And next one is phase. Phase of a vibrating particle at any instant gives the state of the particle as regards its position and the direction of motion at that instant. Okay, phase means it gives about where that object is at that particular instant. To get an idea that if we know about the phase of the particle, we can say that at that instant where that object is. And it is equal to the argument of the sine or cosine function. What is meant by argument? Argument means angle, no? So it is the angle of the sine or cosine function. So here, if that is a solution that already we discussed, x is equal to a cos omega t plus phi 0. So here, which is the argument? Omega t plus phi 0 is the argument. No? So phase of the particle can be written as omega t plus phi 0. So how we will know about the displacement of the particle? That we can check by this table. So if omega t plus phi 0 is 0, what is the displacement? X is equal to a cos 0. So that is equal to a. Then if omega t plus phi 0 equal to pi by 2, what is the value of x? X equal to a cos pi by 2, which is equal to 0. Similarly, if omega t plus phi 0 is pi, x value you will get it as minus a because cos pi is minus 1. Similarly, if you are substituting omega t plus phi 0 as 3 pi by 2, you will get x equal to a cos 3 pi by 2, 3 pi by 2, cos 3 pi by 2, again 0. Then last one, when x equal to omega t plus phi 0, which is equal to 2 pi, x is equal to a cos 2 pi, again you will get as plus a. Okay. So that is a significant. That's why by knowing the phase, we can get an idea about the distance, or we can get an idea about the displacement of the particle at that particular instant of time. That is the significance of phase. And next one is initial phase or epoch. The phase of the vibrating particle corresponding to the time t equal to 0. At t is equal to 0, what is the angle? That is known as initial phase. Okay. So in this case, we can see that omega t plus phi 0, that is the phase. So at t is equal to 0, what will be the value? Omega t, that term will be 0. So only phi 0 will be there. So initial phase is given by phi 0. Okay. So x equal to a cos omega t plus phi 0. In that, x stands for displacement, a stands for amplitude, that already we discussed, maximum displacement of the particle. So a has the same unit as that of x, and omega stands for the angular frequency or angular velocity. T means at any time, that at any instant of time, and phi 0 is the initial phase. This expression x equal to a cos omega t plus phi 0 is very, very important. Okay. Now we will discuss about uniform circular motion and SHM. Is there any relation between uniform circular motion and SHM? If we tie a stone to the end of a string and move it with a constant angular speed in a horizontal plane about fixed point, the stone would perform a uniform circular motion in the plane. Already you know that if you are tying a stone at the end of a string and if you are moving it with a constant angular speed in a horizontal plane, what happens? That object will perform uniform circular motion. But if we observe the stone sideways, the stone will appear to perform a to and fro motion along the horizontal line with the other end of the string as the midpoint. This is very important. If we observe the stone sideways, we can see that it has a to and fro motion. Along with this, one animated video is shown here. After watching this class, you can see that video also. Then you will come to know clearly about what is the relation between uniform circular motion and simple harmonic motion. Okay. So here we are considering an object is moving in a circular path. A is the radius. Okay, capital A stands for the radius, and at a particular instant of time, that at t equal to 0, that object is at the position P. So that time phase angle, initial phase angle is phi, and after some time what happens? It reached to a position Q. So that time angle is given by omega t. Okay. That is the diagram. So in the figure we can see the motion of a particle P executing a uniform circular motion of radius A with a constant angular speed omega. It is moving with a constant angular velocity omega. So at any instant the angular position of the particle is given by omega t plus phi, because phi is the initial phase, initial angle. So we define the projection of the particle on the x-axis in terms of another particle. So projection of the particle on the x-axis can be written as, how we can write, if you are writing it as ON will be equal to, how you can write ON is equal to, where O is the center of the circle. Okay, so ON can be written as OQ. ON by OQ is equal to cos omega t plus phi. Can we write? Adjacent side by hypotenuse. Adjacent side is ON and O. What is O? O is the center of the circle. It is not marked there. You can consider it. Okay. So ON by OQ is equal to cos omega t plus phi, or ON can be written as OQ into cos omega t plus phi, or that can be written as, what is OQ? OQ is the radius of the circular path that we considered it as A. So we got it as projection. It is along the x-axis, that's why we are writing it as, instead of ON we can write it as x. So x of t at any instant of time, x of t, that displacement is equal to A cos omega t plus phi, and that is the solution of simple harmonic motion. So we can say that the projection of uniform circular motion on either x-axis or y-axis corresponding to the simple harmonic motion. Okay, so same way it's y projection along that, what you will get it as A sin omega t plus phi. Okay, so the position vector of particle which is undergoing simple harmonic motion. And now we will say that same sentence only, once again it is written. So simple harmonic motion is the projection of the uniform circular motion such that the center of uniform circular motion becomes the mean position of the SHM, and the radius of the circular motion is the amplitude of the SHM. Okay, so that is the significance. And now here you can see sometimes problems will be asked like this. So in this first case you can see that object is at this position, initially it is at a position B. So that time initial phase angle is phi 0. After some time it reached position P. It is rotating anti-clockwise direction. So omega t, phase will be omega t plus phi 0. Here in this first case, what you can see, initially object is at this position A. So phi 0 it is downward. Okay, and after some time it reached position P, that angle omega t. So in that case phase will be omega t minus phi 0, and in second case you can see phase is omega t plus phi 0. Okay, so in both cases it is shown as anti-clockwise direction. So normally anti-clockwise direction we are considering it as positive. Okay, so here we can see that in the given figure it corresponds to circular motion. Circular motion is given, the radius of the circle, the period of revolution, and it is mentioned it is anti-clockwise are shown. Obtain the corresponding simple harmonic motion of the x projection of the radius vector of the revolving particle. Okay, what it is given at t equal to 0, object is at this position P, which means it makes an angle pi. Makes an angle pi. Now time period, we know time period is given, it is 4 seconds, and radius of the path it is given 2 meter, and we know the formula. What is the formula? X equal to A cos omega t plus phi, and instead of omega we can write it as 2 pi by t into t plus phi. Time period, all data is given. So if you substitute, what you will get? 2 cos 2 pi t by 4 plus phi. So 2 by 4 you will get it as half. So pi by 2t, and cos pi plus theta can be written as cos theta, because in the third quadrant cosine function is positive or negative. It is negative. Because in the third quadrant only tan and cot function is positive. So in the third quadrant, since cosine function is negative, cos pi plus theta we will get it as minus cos theta. So x equal to minus 2 cos pi by 2 t. Unit is in meter. Okay. Next one, a simple harmonic motion, not a harmonic motion is represented by x equal to 10 sine 20t plus 0.5. Write down its amplitude, angular frequency, time period, initial phase. If displacement is measured in meters and time in seconds. These type of problems normally will be asked. So what we have to do, we have to compare it with the standard equation x equal to a sine omega t plus phi 0. So if you compare with the standard equation, you can write directly amplitude is equal to 10 meter and angular frequency omega is equal to 20 radians per second because all are in SI units. No. Then frequency, you can find frequency is equal to omega by 2 pi, which is equal to 20 by 2 pi. So 10 by 3.14, 20 by 2 you can write it as 10. So 10 by pi, which is equal to 10 by 3.14. If you simplify, you will get it as 3.18. Unit is hertz. Now you can find time period. Directly you can write 1 by 3.18 or you can write 2 pi by omega, which is equal to 3.14 by 10 or which is equal to 0.314 seconds. Then initial phase, that is phi 0, no, that is given 0.5, and what is the unit? Is this angle? So the unit is radian. Okay. So like these type of problems will be asked. So sometimes instead of omega, they may give it as 2 pi by t into t, like that also, or 2 pi f or 2 pi nu t, like that also they may give. So you have to write, you have to compare it with the standard equation and you have to find the angular frequency or whatever it is asked. Now we will discuss about the velocity of the particle executing simple harmonic motion. So to get an expression for the velocity, we are starting from the expression of displacement. Displacement is given by a cos omega t plus phi. X is displacement vector. Velocity can be written as dx by dt. If you differentiate, what you will get? Minus a omega sin omega t plus phi. No. So velocity is given by minus a omega sin omega t plus phi. So instantaneous velocity, we can write it as minus a omega sin omega t plus phi. So here you can see that in that graph, okay, velocity, maximum velocity is given by a omega, that is shown along the tangential direction. What is the maximum velocity? When omega t plus phi is equal to pi by 2. No? That is when sine function takes maximum value, that is 1. So that time maximum velocity is given by a omega. Okay. So we can say that, and v of t, that is the velocity at any instant of time. So in the above figure, we can see the velocity of the particle is the projection of the velocity of the reference particle. Okay. Again, velocity we can represent in another way also. How? Minus a, instead of sine theta, we can write it as root of 1 minus cos square theta. No? So minus a omega into root of 1 minus cos square omega t plus phi, and cos omega t plus phi can be written as x by a. So what you will get? Minus a omega into root of 1 minus x square by a square. And if you simplify, what you will get? Minus, that is, if you take the LCM, what you will get? A square minus x square by a square. And if a square comes from the root, a will be there in the denominator. Both a will get cancelled. So you will get velocity as minus omega into root of a square minus x square. Okay, sometimes problems will be asked based on this also. What is the velocity of the particle? If the displacement at that instant is, particular displacement is given, angular frequency will be given, amplitude is given. So you can use this formula. Okay. Now next one is related to acceleration. So we are starting from the expression of displacement itself. Displacement is given by a cos omega t plus phi. Velocity is, if you differentiate it once, you will get minus a omega sin omega t plus phi. Again, if you differentiate, you will get acceleration. So acceleration is equal to dv by dt. So what you will get? Minus omega square a into cos omega t plus phi, and a cos omega t plus phi can be written as x. So we can write acceleration is equal to minus omega square x. So we can say acceleration is proportional to displacement. No. And it is always directed towards the center, that already we discussed. In circular motion, center means mean position of the simple harmonic motion. So if we are representing velocity, displacement and acceleration, how it will be, that only we are discussing here. Okay. So displacement, here we are showing by sine function. It can be either sine function or cosine function. Okay. Displacement, here we are showing it as sine function. Okay. A sine omega t plus phi, and acceleration and velocity all are shown like that. You can see that table. Okay, either it can be cosine or sine function. Here we are displacement we are showing by sine function. Automatically velocity will be cosine function. Acceleration again it will be sine function with one minus sign. Okay, so here you can see that maximum value of displacement is A, maximum value of velocity is A omega, and maximum value of acceleration is A omega square. Okay, is it clear? So that is the graph. Either it can be sine or cosine function. Here we are showing for sine function. Now another problem. A body oscillates with SHM, simple harmonic motion. According to the equation is given x equal to 5 cos 2 pi t plus pi by 4. At t is equal to 1.5 second. Calculate the displacement, speed and acceleration of the body, and all quantities are given in SI units. Omega angular frequency is given. How you can compare it with the standard equation? X equal to A cos omega t plus phi 0. So amplitude is 5, omega is 2 pi second inverse, and time period is 1 second. Okay, is it clear? Okay, why omega is equal to 2 pi, and omega can be written as 2 pi by t. So 2 pi by t is equal to 2 pi, so t is equal to 1 second. Now at t is equal to 1.5 second, we have to find the displacement. So you can substitute t is equal to 1.5. So 5 into cos 2 pi into 1.5 plus pi by 4. So 5 into cos 3 pi plus pi by 4. So what you will get? You will get it as minus 5 into 0.707, and if you simplify you will get it as minus 3.535 meter. I am not telling in detail because we have studied already in trigonometry how to find the value, and those who are not taken maths you can write up to this 5 cos 3 pi plus pi by 4, up to that enough. Okay, meters. Now we can find the speed. How to find, that is the formula. Speed is equal to minus A omega sine omega t plus phi 0. No? So A amplitude is given by 5 and omega is 2 pi, sine 2 pi into 1.5 plus pi by 4. So what you will get, sine 3 pi plus pi by 4. If you simplify you will get it as 10 pi into 0.707, which is equal to 22 meter per second. Now acceleration is given by minus omega square into x, minus omega square displacement. So minus 2 pi, omega is given by 2 pi whole square into displacement, already we know that. So minus 2 pi whole square into displacement, we got it as minus 3.535. So acceleration we got it as 140, what is a unit, meter per second square. No? Now we will discuss about energy in simple harmonic motion. Okay. So kinetic energy of the particle which executes simple harmonic motion, that already we know the formula. Kinetic energy is given by half mv square, and velocity we know that A omega sine omega t plus phi, that already we discussed. So what you will get, kinetic energy is given by half m omega square A square sine square omega t plus phi, and that can be written as omega, but k by m is equal to omega. So m omega square can be written as k. No, that is known as spring factor or force constant. So kinetic energy is given by half k a square sine square omega t plus phi. Now we have to find potential energy. Potential energy is given by half kx square. Half kx square, that already we discussed in the case of spring. No. That work energy and power, that chapter already we discussed. The potential energy associated is given by half kx square. So half, instead of x is the displacement, x can be substituted as a cos omega t plus phi. So potential energy is given by half k a square cos square omega t plus phi. So total energy we can find whether it remains same or not, that we have to check. No? So total energy is given by potential energy plus kinetic energy. Kinetic energy is given by half k a square sin square omega t plus phi, and potential energy is given by half k a square cos square omega t plus phi. So what you will get, half k a square can be taken common. So sin square omega t plus phi plus cos square omega t plus phi, which is equal to 1. So total energy we got it as half k a square. No. So k is constant. K means that force constant, that is for a given system it is constant, and a amplitude also will be constant for a given particle which is executing simple harmonic motion. So we can say that total energy is always constant. Okay. So the kinetic and potential energy in a simple harmonic motion varies between 0 and their maximum value. So kinetic energy, if we are representing kinetic energy as a function of time, but we can see that you can see a graph like this, no, but total energy will be always remain same, and both kinetic energy and potential energy repeats after a time t by 2. No, after a time t by 2 the same graph will be repeated. Okay, is it clear? So total energy you can see it we are showing by straight line. Potential energy will be maximum at mean position, and kinetic energy will be minimum at the mean position. Okay, is it clear? So that only here we are showing the graph in kinetic energy, potential energy and total energy as a function of time only, not as a function of displacement. Okay, next we are going to discuss that only. So here we can see that kinetic energy will be maximum at mean position, and potential energy will be minimum at mean position, maximum at extreme position. Why? At extreme position only half k x square x will be equal to amplitude. No. So at the mean position, what is the value of potential energy? Potential energy is given by half k x square. Displacement is 0 at mean position. So at mean position kinetic energy is maximum, and at extreme position potential energy is maximum, and total energy remains same. So this graph corresponds to variation of energy with a displacement, okay, as a function of displacement. Okay, so I hope all of you understood what we discussed about oscillations, and you can go through those topics in detail, and if you are having any doubt, communicate that to me. Thank you.